Good morning, students. Today we are going to discuss module number 1, that is basic concepts. Here we are going to discuss about that series and parallel network reduction method and its problems. So to discuss about that series and parallel network reduction technique, here I am going to take that reference as one problem. So look at the problem, find out the equivalent resistance for the network shown in figure. So here there are resistors in the given problem. For suppose if you look at this problem consists of a 4 ohm resistor. Again it is connected in parallel with 2 ohms resistor. Again it is connected in parallel 6 ohms and 3 ohms, 1 ohm and 5 ohm and 8 ohms. I want to know that what is the relation between 4 ohm, 2 ohm, 8 ohm, 6 ohm, 3 ohm, 1 ohm, 5 ohm. And I want to find out the equivalent resistance for the network shown in figure according to the given problem. So I want to find out, I want to reduce that complexity of this network, and I want to say that what is its equivalent resistance, R equivalent value. I want to reduce this all resistors into a single resistance value. How it is possible to find out the single resistance value? The single resistance value, how we can find out whose value is equal to R equivalent. This R equivalent value, how we can find out here means, let us analyze the circuit with the currents. So I am going to imagine there is a voltage source across these two terminals. Like now this voltage source drives a current called I into the circuit. Now this current I is now this current I is going to divide it into some other currents. Some other currents like I is going to divide it into some other currents as I1, I2. Now again this I2 is divided into another two currents, name it as here I3 and I4. So I2 is going to divide into another two currents, name it as I3 and I4. What about I1? I1 is not going to divide anywhere. I1 is the current which is commonly flowing 1 ohm and 5 ohm resistor. Therefore 1 ohm and 5 ohm resistors are connected in series. 1 ohm and 5 ohm are connected in series, and again here I3 and I4 are connected in parallel. So I3 and I4, I3 is flowing in 6 ohm resistor and I4 is flowing with 3 ohm resistor. Therefore, what about the relation between 6 and 3 here? The relation between 6 and 3 in the given problem, in this problem, the relation between this 6 and 3, these two are connected in parallel. Therefore, the equivalent resistance when the resistors are connected in parallel like 6 ohms and 3 ohms, that is 6 into 3 divided by 6 plus 3, it becomes 2 ohms. 18 divided by 9, 9 ones are 9 twos are 18 ohms. So the equivalent resistance is 2 ohms. Now I am going to replace this 6 ohm and 3 ohm resistor with a value of 2 ohm resistor. Here, this is the way how I am reducing the complexity. Instead of that two resistors like 6 ohm and 3 ohms, I am replacing it by a 2 ohm resistor. Now I reduce that complexity of the circuit from the above circuit to, this is the given circuit figure A. Figure A to figure B, these two resistors which are connected in parallel, that complexity I am reduced into a single resistor like 2 ohms. Now apart this one in figure A, what is there any difficulty? There is one more difficulty here, the relation between 1 and 5 ohms. The relation between 1 and 5 ohms, here those two are connected in series. How? Just now we analyzed that there is a current I, there is a current I is divided into two currents, name it as I1, another one is I2. I1 is the current which is commonly flowing 1 ohm and 5 ohm here. Therefore these two are connected in series. Therefore 1 plus 5, that is equal 6 ohms. Now I am going to replace this 1 ohm and 5 ohm with a single resistor called 6 ohm resistor here. Again I reduce the complexity figure A to figure B. So figure A to figure B, in figure A, 6 ohms, 3 ohms are connected in parallel. I reduce the two resistors into single resistor whose equivalent resistance is equal to 2 ohms here. Here 1 ohm and 5 ohm are connected in series. So whose equivalent resistance is equal to 6 ohms. Now come to figure B. In figure B, again we have to perform the relation one resistor by another resistor by analyzing the currents. Now I am assuming that a current I is flowing through that figure B circuit. I is divided into two currents at this node, namely called as I1, which is flowing through 6 ohm resistor, I2, which is commonly flowing these two 2 ohms resistors. One is this 2 ohm and the one is another 2 ohm. Now what is the relation between these two 2 ohms? The relation between these two 2 ohms, that is the current is same, therefore these two are connected in series. If these two are connected in series, then equivalent resistance 2 ohm plus 2 ohm is equal to 4 ohm. Now I want to replace these two 2 ohm resistors with one 4 ohm resistor, that is its equivalent resistance value. So now I replace that two 2 ohm resistors with one 4 ohm resistor, and again that 4 ohms is, what about the relation with another 6 ohm resistor here? As we saw that there is a current I up to this node. This current I is divided into two currents. One is the current I1 which is flowing through 6 ohms. I2 is the current which is commonly flowing these two 2 ohm resistors. One is this 2 ohm, other one is another 2 ohm. So these two are connected in series, therefore its equivalent resistance is equal to 4 ohms. Now let me tell what is the relation between 4 ohms and 6 ohms. 4 ohms and 6 ohms, it is parallel because here the current is I1, there the current is I2. If it is connected in parallel, what about the equivalent resistance formula? If it is connected in parallel, the equivalent resistance formula, 4 ohm is connected in parallel with 6 ohm, that is 4 into 6 divided by 6 plus 4. 24 divided by 10, it is 2.4 ohms. Now I want to replace this 4 ohm resistor and 6 ohm resistor with a single resistance value whose value is equal to 2.4 ohms, which has been shown in figure C, that is 2.4 ohms. After replacing that and placing 2.4 ohms, now let me tell what is the relation between these 4 ohms and 2.4 ohms and 8 ohms. The relation between 4 ohm, 2.4 ohm and 8 ohm, what is means here? If you analyze the currents here, the current which is commonly flowing here, therefore these three are connected in series like 4 ohms plus 2.4 ohms, 8 ohms. 4 plus 2.4 plus 8 ohms, it is equal to 14.4 ohms. Therefore the overall equivalent resistance R equivalent, the overall equivalent resistance, that is R equivalent value is equal 14.4 ohms. I hope that everyone understood up to here. Let us go through that one more problem. Look at the problem which has been shown at figure. This is problem number 2. They are asking that find out the equivalent resistance for the network shown in figure. In this network I want to find out the equivalent resistance. In this network, how to find out the equivalent resistance? Let me know the relation between one resistor by another resistor. Just imagine the current I is there. This current I is divided into two currents, namely called as I1 which is flowing through 6 ohms. I2 is the current which is flowing through 3 ohms. Again this I2 is divided at this node. One current is flowing I3 in 4 ohms and I4 is the current which is flowing this 4 ohms, 5 ohms and 3 ohms. Therefore I4 is the current which is commonly flowing between these 4 ohms and this 5 ohms and this 3 ohms. That means this 4, 5, 3 are connected in series. If 4 ohms, 5 ohms and 3 ohms are connected in series, then equivalent resistance value 4 plus 5 plus 3 is equal to 12 ohms. So 4 plus 5 plus 3 is equal to 12 ohms. Now I am going to replace that figure A into figure B, whose equivalent resistance value is equal to 12 ohms. So now I am replace that figure A2 as figure B. 4 plus 5 plus 3 replaced as 12. Now in this circuit, again, what is the relation between one resistor by another resistor in the given network of figure B? In figure B, if I want to know the relation between, let us start again. There is a current I. I is divided into two currents. I1 is the current which is flowing through 6 ohms at this node onwards. I2 is the current which is flowing through 3 ohms. I2 is again divided into two currents, I3 and I4. I3 is flowing through 4 ohms and I4 is the current which is flowing through 12 ohms. Therefore, this two branches the current is different, one is I3, another one is I4. Therefore these 4 ohms and 12 ohms are connected in parallel and its equivalent resistance value is equal to 3 ohms. How we got the equivalent resistance is equal to 3 ohms means R equivalent is equal here 4 is parallel with 12, 4 into 12 divided by 4 plus 12, 48 divided by 16, 16 ones, 16 threes. So total it is 3 ohms. Now I am replacing these two resistors with a single resistance value whose value is equal to 3 ohms. Now what is the relation here in figure C? The relation in figure C, there is one resistor by another resistor. Again imagine there is a current I which is driven by the voltage source, and I1 is divided into two currents, namely I2 is the current which is commonly flowing through the 6 ohms and I3 is the current which is commonly flowing through this 3 ohms and 3 ohms. Therefore these 3 and these 3 the current is same, therefore these two are connected in series. If it is connected in series, then R equivalent value is equal 3 plus 3, that is equal 6 ohms. Now I want to replace these two with 6 ohm resistor which has been shown in figure D, that is here 6 ohms. Now again this 6 ohm and this 6 ohm are connected in parallel because a current I is divided into two currents. One current is flowing through this 6 ohm, another current is flowing through this 6 ohm. Therefore 6 ohms and 6 ohms are connected in parallel means 6 into 6 divided by 6 plus 6. 6 into 6 divided by 6 plus 6, 36 divided by 12. 12 ones are 12 threes are. So the equivalent resistance value is equal to 3 ohms. Now I want to replace these two 6 ohms with a single resistance whose value equal to 3 ohms. Now I am replaced that figure D to figure E. Here these two are replaced by 1 3 ohm. Now what is the relation between this 4 ohm, 3 ohm and one more 3 ohm here? Let us imagine a current I which is commonly flowing this 4 ohm, 3 ohm and another 3 ohm. Therefore these three are connected in series and its equivalent resistance value. The equivalent resistance value R equivalent here, if it is series, that is 4 plus 3 plus 3, that is equal to 10 ohms. Now I am going to replace figure E with one more figure, name it as figure F, whose resistance is only one resistance value, whose value is equal to R equivalent, that is equal 4 plus 3 plus 3, that is equal to 10 ohms. This is the ultimate answer for the given problem. Thank you all.